first function and the q norm of the second function, where p and q are such that 1 over p plus 1 over q is equal to 1. And the hard work was done last time, really. So for p strictly between 1 and infinity, we proved this inequality last time, and we used the Young's inequality to do that. So only the case p equals infinity or q equals infinity is left. Note that if p is infinity, then because 1 over p plus 1 over q has to be 1, if p is infinity, then q must be 1, and the other way around. So without loss of generality, we can just treat the case p equals 1 and q equals infinity. Right? If p is infinity, then q has to be 1, and the inequality is symmetric in p and q. So let's assume p is 1 and q is infinity. Then the proof is much simpler than in the previous case. It's just a one-line computation, basically. So if we write down integral fg, then q is infinity, so g is in L infinity, which means that g is essentially bounded. So in this integral, we can replace, we just leave f as it is, and we can replace g by its infinity norm, and that only makes it larger, right? But now, in this integral, this infinity norm of g, that's just a constant. We can move that in front of the integral. So this is the same as norm g, integral mod L d mu, but this is just the same as infinity norm of g times L1 norm of f, right? This is just the integral of the absolute value of f. And that's precisely Hölder's inequality for p equals 1 and q equals infinity. So it's really simple. You just replace g by its essential supremum, and that only makes it larger, and then everything falls into place. So this was very quick, and this completes the proof of Hölder's inequality. Are there any questions about this proof or about last lecture? Okay, so if that's clear, then we can start discussing some of the exercises. From sheet 7. And one thing I want to do is the third exercise. Because I think the point that this exercise makes is important to remember. So I'll write down the exercise first. So f is in L1 of R with a Lebesgue measure. F is a function such that it's 0 when x is less than 0. And then we had to show that the integral from 0 to infinity f dm is the same as the limit n to infinity integral from 0 to n f dm. So this was part A. And part B was to find an example of a function f such that this limit n to infinity integral from 0 to n exists, but the function is not in L1. Okay, so part A says if the function is in L1, then this limit exists and it's equal to the integral from 0 to infinity. But if this limit exists, part B, if this limit exists, the function does not have to be in L1. So you have to, in part A, it's important to assume this. Okay, and the solution goes like this. For part A, it's quite short. One can use, for example, the dominated convergence theorem. Because we can define, for example, Fn, a sequence, to be the characteristic function of the interval from 0 to n times f. Then the absolute value of the Fn is bounded by the absolute value of f for every n, right? So we have this integrable upper bound that we need for the dominated convergence theorem. And the second thing we need is Fn converges to f pointwise. But that's also true, right? We just multiply by a characteristic function that converges to 1, so Fn converges to f. And below 0, Fn is always 0, but f is also 0 for x less than 0. So this sequence Fn converges to f pointwise. Okay, and now we check the two conditions. So we can apply the dominated convergence theorem. Which gives us that limit n to infinity integral of Fn, so chi 0 to n times f is the same as integral limit n to infinity chi 0 n f dm. But now inside this integral, this limit is just f. Well, f times characteristic function from 0 to infinity okay, and this is the same as the integral from 0 to infinity f dm. And that's exactly what we wanted to prove. Right, so this is the left-hand side of this equation, and this is, by definition, of the integral from 0 to n, this is the right-hand side. So this is another nice application of the dominated convergence theorem. I hope I've convinced you that the dominated convergence theorem and the monotone convergence theorem are really, really useful in practice. Okay, so this was part A. And part B was to find a counterexample of this if f is not in L1. So, so we want this limit to exist. So f has to be integrable on an interval of finite length, but not on an interval of infinite length. And one example that works is the following. This function. So you take the characteristic function of an interval of length 1, which starts at n minus 1, and then on that interval you make it equal to minus 1 to the power n divided by n. So this would look something, the graph of this function would look something like this. It starts at 0, where it has the value plus 1, minus 1. So it's a constant here, equal to minus 1, and then on the next interval it would have the value plus 1/2. Then it's minus 1/3, and so on. So that's what this function looks like. And then, of course, if we look at this limit of integrals, limit k to infinity integral from 0 to k f dm, well, if we forget about this limit for a second, then this integral, that's just an integral of a simple function, right? Because I'm only going from 0 to k, so if I only look at this function up to a finite k, okay, it's not exactly, it's a difference of simple functions, because it can be negative. But still, the positive part and the negative part are both simple functions if I only go up to a fixed k, right? So we can use the integral for simple functions to compute this this integral for every k. It's just this constant value times the length of the interval, which is 1. So this is limit k to infinity sum n equals 1 to k minus 1 to the power n divided by n. Okay, and this is just the alternating harmonic series, which we know from real analysis. So first we know that this limit exists, and you can even look up the value. It's minus log 2. So it's definitely finite. Okay? And that's essentially because, okay, if you go to a finite k, you can compute this, and positive and negative contributions cancel in a nice way, such that the limit in the end is finite. Okay. Okay, so this is the first part of exercise B. We found a function such that this limit of integrals exists. And now we have to show that f is not in L1. And f not being in L1 is equivalent to this integral being infinite, right? Because f is in L1 if and only if the integral of the positive part of f and the integral of the negative part of f are both finite, which is the same as to say the integral of the absolute value is finite. So if this is infinite, then f is not in L1. Okay, but we can just compute this by the same reasoning as above here. The absolute value of f looks like this, but all the steps are positive. And then if you only go to a finite k, okay, so I went slightly too fast. So this integral is certainly larger or equal than the integral from 0 to any finite k of the absolute value of f, because it's a non-negative function that I'm integrating. And now this integral from 0 to k is just the integral of a simple function, so we can easily compute it. Just this value times the length of these intervals. So this is the same as this, but without the -1. N equals 1 to k, 1 over n. But this holds for every k in n, right? Because this integral goes to infinity, and here I'm only integrating to a finite k. Well, but this is the harmonic sum, and this diverges for k to infinity. So because this inequality has to hold for every k, the left-hand side has to be infinite. Mod f, sorry. Okay, so it's not in L1. So this finishes the exercise, and I just want to comment again on the significance of this. So we've had one theorem that said every Riemann integrable function is also Lebesgue integrable, and then the integrals are the same. But this was only true for functions which are bounded on a bounded interval. Those functions are, if they are Riemann integrable, then they are Lebesgue integrable. And I said already that if a function is improperly Riemann integrable, so on an infinite interval, then that does not mean that the function is Lebesgue integrable. And this is precisely one counterexample that shows this, right? This limit here, this is precisely the improper Riemann integral of f, right? Improper Riemann integral means you integrate to a finite number compute the integral, and then you let this number go to infinity. And the limit that you get is called the improper Riemann integral. So this is an example of a function for which the improper Riemann integral exists, but the function is not Lebesgue integrable. And the reason is for this difference is the difference in definition between improper Riemann integral and Lebesgue integral. The improper Riemann integral was defined as this limit. So if there are positive and negative contributions that cancel, then you can get something finite, and the improper Riemann integral exists. But the definition of the Lebesgue integral was such that the integral of the positive part and the integral of the negative part individually have to be finite. So first you compute the positive part, and that has to be finite. Then you compute the negative part, the integral, that has to be finite. And then you compute the difference of the two. So there can't be any, in the Lebesgue definition, there can't be any cancellations between positive and negative that make the thing finite in the end. So yeah, in this sense, the definition of the Lebesgue integral is more restrictive. And that's why examples like this exist. Yeah, so that's one thing that I wanted you to remember about Riemann and Lebesgue integrals. Yeah, so this was exercise 3, and I'm going to do exercise 4 too, just after this one, because there exists a very short and nice solution that one of you found actually of this exercise. So are there any more questions about exercise 3 before we continue? Okay, if not, okay, I'm only going to do exercise 4b because 4a is quite similar. Okay, so in exercise 4b, the measure space was Rn. The sigma algebra was just the power set of Rn, and the measure was the Dirac measure at 0. And then I'm going to write down a short version. Then we had a function from R to R. And basically the task was to show that any function from R to R is integrable. And the integral, and in the hint, there the task that there was this formula, integral of f d delta 0 is just f of 0. And there are different ways of doing this, and actually in this solution that I'm going to put online on Learning Central, I did it by approximating f with simple functions, and yeah, that's sort of a standard way to do it. Then you can. I'm not going to explain it. Then you can derive this formula. You can look at it if you like. And this solution, I didn't write this down in LaTeX and put it online. I'm just going to show it to you now. This solution is much simpler and much shorter. So first, let's check measurability of f. If we want to show integrability, first it has to be measurable. But measurability is clear. because f measurable means that the pre-images of half-lines have to be measurable. But in our sigma algebra, everything is measurable, every set. So every function is measurable. Okay, now integrability. As I said before, we have to check the integrals of f plus, the positive part, and f minus, and they both have to be finite. So if we write down the integral of f plus with respect to delta naught, now this is the integral for non-negative measurable functions. And in the section about integral of non-negative measurable functions, we showed that this integral is additive, right? So we can do the following. This is the same as integral Rn characteristic function of Rn minus 0 times f d delta naught plus integral Rn characteristic function of 0 f. Okay, so just decompose f into basically its value at 0 and everything else. And this makes, so this is useful because the measure that we're considering is the Dirac measure at 0. So every set that does not include 0 is a null set, has measure 0. So in fact, this function is 0 almost everywhere, right? And this function, that's a simple function, right? It's 0 everywhere except in 0. And at 0, its value is, oh sorry, this should be f plus everywhere, sorry. At 0, the value of this function is f plus of 0. But the important point is, this is 0 almost everywhere. This is a simple function. Which means that the first integral is just 0. And the second integral is easy to compute because for the integral of simple functions, we have this formula which just says the integral is f plus at 0 times delta naught of 0. Right, and delta naught of the set 0 is equal to 1. So this is f plus of 0. Okay, so this was f plus, and for f minus we can do exactly the same calculation. And we will get that the integral of f minus is equal to f minus of 0. So this shows integrability because f plus of 0 and f minus of 0, of course, are both finite, are some real number. And then, by definition of the integral of f is just the integral of f plus minus the integral of f minus. So it's f plus of 0 minus f minus of 0, which is f of 0. So yeah, this Dirac measure is just such a simple thing that we could, in a few lines, we could derive a formula for its integral of any function. Okay, so now we know how to do that. Are there any questions about exercise 4? Okay, if not, we continue with the lecture. So, we're in the section about integral inequalities. And there's a reason why the section is called integral inequalities. So we've had Jensen's inequality, we've had Hölder's inequality, and the next theorem is Minkowski's inequality. Okay, and the statement is, start with the measure space, x sigma mu, and let P be between 1 and infinity. Then if f and g are functions in LP of x sigma mu, then f plus g is in LP I guess we have to assume that f and g are finite valued, so f, g go from x to r. Okay, so then f plus g is in LP as well, and the following inequality holds. The p norm of f plus g is less or equal to the p norm of f plus the p norm of g. So it's basically it's the triangle inequality for the LP norm. That's what Minkowski's inequality is. And indeed, if in the case p equals 1, it's really simple. It follows immediately from the usual triangle inequality for real numbers. Just because on the left-hand side you have absolute value of f plus g integrated. On the right-hand side you have absolute value of f plus absolute value of g. So this inequality just becomes the usual triangle inequality integrated on both sides. So for p equals 1, it's clear. And now we're going to distinguish two more cases. First, p strictly between 1 and infinity, and then later we'll consider p equal to infinity, but that's going to be nice and short again. So for p between 1 and infinity, so the idea of the proof is to use Hölder's inequality, basically. So we choose the conjugate exponent to p. So choose q to be 1 minus 1 over p inverse, which is the same as p divided by p minus 1. Then one can check that 1 over p plus 1 over q is 1. So for this pair p and q, we can use Hölder's inequality. So now let's start with the p norm of f plus g. So this left-hand side to the power p. This is, by definition, the integral of absolute value f plus g to the power p d mu. And now, because p is strictly larger than 1, we can do the following. This is the same as integral f plus g times f plus g to the power p minus 1, right? And now the exponent of the second factor is still positive because p is larger than 1. Okay, now we use the usual triangle inequality in this first factor to get that this is less than integral mod f times f plus g to the power p minus 1 d mu plus integral mod g times f plus g to the power p minus 1. Okay, and now in each of these two factors we can use Hölder's inequality. So this last line is less than by Hölder's inequality is less than the p norm of f times f plus g to the power p minus 1, the q norm of that, plus the p norm of g times this thing again, f plus g to the power p minus 1, and yeah, the q norm of that. Yeah, so maybe just as a sanity check, let's look at this integral. F is in LP by assumption. And then this function, f plus g to the power p minus 1, this function has to be in LQ. if we want to apply Hölder's inequality, right? But by definition of Q, this sum to the power Q is just F plus G to the power P, right? Because the P minus 1 cancels. So F plus G to the power P minus 1 is actually in LQ. So these LQ norms here are well defined, and we're allowed to apply Hölder's inequality. So we really have this estimate.
What norm of G is it? But it looks like you've written the G norm of G.
Oh, that's true. Sorry. That's the LP norm. Sorry, yeah. Yeah, the LP norm is the only thing we're allowed to write down because G is in LP by assumption. And we don't know anything else about G. Okay, yeah. And now this is F times this long thing, and G times the same long expression. So this is norm F, P plus norm G, P times yes, and now I'm gonna write out this LQ norm. So that's integral F plus G to the power Q times P minus 1 d mu, and then the whole thing to the power 1 over Q. Okay, so this was just inserted definition, and now this exponent Q times P minus 1 is P, right, by the definition of Q. So this is the same as norm F plus norm G times integral mod F plus G to the power P d mu, and then this exponent 1 over Q is the same as P minus 1 divided by P. Okay, so now this integral here, that's just the LP norm of F plus G to some power. And now remember what we started with. We started with the LP norm of F plus G to the power P. So we can just divide by this factor, and okay, first we can even simplify this even further. So this is norm F P plus norm G P times what I just said, F plus G, the P norm to the power P minus 1, right? Because the 1 over P is included in the definition of the LP norm, so the power P minus 1 is left. Okay, so we have this LP norm to the power P minus 1 on the right hand side, and to the power P on the left hand side. So we can just divide by this, and we get Minkowski's inequality. Okay, so this is the case P strictly between 1 and infinity. And then there's only one case left, which is p equal to infinity. So now we have to take L infinity norms everywhere here. So the essential supremum of the absolute value. But this is easier than the previous proof because we can use the normal triangle inequality again. So we have this from the usual triangle inequality. This implies that absolute value of f plus g is less than infinity norm of f plus infinity norm of g almost everywhere. Because the essential supremum has this property, right? And if this is larger than this, then the essential supremum of this is larger than this almost everywhere. Okay, but now we can just take this inequality and take the essential supremum again, and we get norm f plus g infinity is less than norm f infinity plus norm g infinity. And that's Minkowski's inequality for p equal to infinity. Okay, are there any questions about this proof?
Could you explain more about in the case that p is between 1 and infinity, why f plus g to the p minus 1 is in LQ? Or like why you can take the q norm of it? So in the holder step. So at the top of that board.
So that's here.
Yeah.
So f plus g to the power p minus 1, it means that if I, so this being in LQ means if I take it to the power q, then it has to be in L1. It has to be integrable. Right?
But how do you know if it's in LQ?
That's what I'm checking. That's what I want to check. So this being in LQ means if I raise it to the power q, it has to be integrable. If I take this and raise it to the power q, then it's f plus g to the power p, right? And f and g are both in LP. Yeah, so we'd still have to check that f plus g is in LP. Did we prove this already or not? I'll think about it in the break. So, but are you happy that this is the only thing that's missing? Okay, so I'll think about this in the break, and we'll have the break now, and then I'll tell you. So see you in 10 minutes.
I found the suitable function. Did you say satisfies the substitution. Basically, if I get that on all of the things, it's that for some reason.
But why do you?
My sub-solution of the of my TV. So my PD is flash. Yeah. Trying to find an area of stability. Well, yeah. So
mean, it did.
I mean, you have the ability to do it.
That's the experiment man conducts.
The problem is, so I've done a linear function here.
Yeah.
Yeah, it's
I need
definitely
curve functions link them, so it's continuously differential. And I've managed to
I thought you might see it as just like function and not like
the same solution as well.
It's fine, I think it's still.
I did that all on my own.
Splendid.
Yes. It's such a sick base that
So I'm not well suited for this because I'm still using GeoGebra. I like going back to it.
To the
It's
classic.
nostalgia. I discovered Desmos yesterday.
prioritization tasks.
Is it Desmos?
Tasks.
I've heard of it.
I discovered it today and it's a lot better. Because you can do piecewise stuff as well. I'm not feeling so good.
To be fair, there aren't many good programs for software.
No. Other than Handle. Yeah, it was just like, yeah, let's prove the second bit. Don't think about the first bit.
Well, in the all-knowingness, the first proof that FSG is never given to it at the start is like the main bit.
And then this is like a result of it.
Prioritize like who was the most acceptable, who was the least, and then like do it
Yeah.
and
Seems that I'm not sure that F plus G in LP is part of the minus inequality, is it? It's not part of that proof.
You don't see that
thing.
Yeah.
Well, there was more into how to describe it
But-
because the guy who was going to do the deal, he wasn't sure of his.
I guess it's
Right, so if
he
F-
just because we haven't proved it before.
do it. So then he
Do you know what?
went
It's
back,
probably a
back from
case
the
of
loan to buy the watch,
adding and
even
taking
though
away
he's
something.
already in his overdraft.
Yeah.
And it's like,
So what you have
the
is
secretary,
if
like,
it's
so
the
him
thing of
buying
F
the Rolex,
thing.
like, so that
If the integral of mod F, the integral of mod G of finite, the integral of mod F plus G, you add something in the middle, split them up.
I think overall,
Nicely.
like, some things went well, some things went bad, so I can't really say.
You get some. Or unless it's just random quality again.
But then next week they said, but it might not be that.
Because you just have to show it's finite, you don't have to show what it is.
More or less, I don't understand what the problem is.
Yeah, but that's quite nice. It was like Birmingham and
About me.
like there's 15 people to only 4.
I've shown now why one of the proofs in the paper over here is wrong.
Did you find a counter example?
But their proof is basically an example because they're trying to show that an inequality is sharp. So they've just come up with a function which attains like the bound. You know what I mean? But that function is contained in L2, which is very important. So we have found a function in L2 that attains this bound. It's not a function in L2.
Not just it's like orange juice is there.
They always do that, like orange juice, but like
Yeah, I don't know what's with orange juice. It wasn't a pint, it was like an was it
I always feel like a bit embarrassed on having it when I'm not drinking. I remember feeling that. It's like when I came to graduation and that's what then everyone else was just like said he's like upset. And I was just there like they're like face.
There's also another mistake, but it turns out to be inconsequential. But it is a disgusting mistake, and the basic idea is that they effectively assume that the complex conjugate of any complex number is equal to its real part.
And that is incorrect.
Of course it's incorrect, yeah. Make a big deal of it as well, like by virtue of the equality, blah 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 blah, and then you effectively you're so fucking wrong. It turns out to be inconsequential, which is a shame.
Is it one of those things that can you imagine like the thick of it, except in a maths department, and then you find that mistake and you bring up the guy who did the proof and what the fuck was that?
Yeah.
You start swearing at him. Why you assume that? Well, I assume you're sorry. Honestly, like massive. He's written a new series
Really?
with Hugh Laurie. It's,
Oh wow.
it's called Avenue 5. It's
Oh
going to
my
be set in
god.
space.
That's gonna be
Space.
Set in space. And it's like, I'm pretty sure he's going to be like the head, like the
I mean,
president.
House
The
literally
president.
is like Hugh Laurie, just like he literally is like the medical version of Malcolm Tucker.
Yeah.
You know?
Yeah, and you can tell in House that they were too scared to say like huge and might totally something down or changes something a little bit. When he like goes off, you can tell there are bits where he's clearly off script. He's just like, nah, we're keeping it in. Don't want to upset Hugh Laurie.
When's it coming out?
He's got a really good blues album.
What?
He's got a really good blues.
Yeah.
He's got a really good album. I'm pretty sure he plays it. Lots of festivals.
And then straight after that.
But it's like, isn't it so ironic that a posh, really well educated white man is singing about the blues? It's like complete opposite of what he established. No, I'm looking forward to that. It's going to be on, I don't, probably like Skylantic HBO or something like that. So I watched it. Next year. It was in like the trailer of like all the things coming out next year on HBO. But it's Hugh Laurie, it's, what's his name, Ian Ucci. And I'm pretty sure, I know that Peter Capaldi has been cast in the Suicide Squad. Praying it's Mr. Freeze. Like, anything with Peter Capaldi I'll watch. He's so good.
Yeah.
What's that blink? You see that blink from space?
Well, I think I'm more comfortable with
Sweaty octopus sign on hook per hour.
Can't get it now. They're always late. That's why.
They're not really that interesting. They're just like.
It's after the interview where he's sat in the car with Jamie.
Yeah, I need like email for them to like reimburse me.
Sweaty Ben.
Blinky Ben.
And I bought breakfast as well. But I have to eat it.
Probably gonna watch Spinners and Lisa's later.
But they both
I haven't seen it in ages. I watched the news. I watched the Newsnight one the other day.
Fair share and sausages and all that. It was a pretty fancy breakfast. Yeah, couldn't finish it all. It's too rich.
Nothing's to understand in our way.
It's going to be classic. You're going to walk in halfway through. Much too big. Much too big. Like 7 or 8.
PhD research going.
I've got to personal statement and CV essay, so actually got some.
Yeah.
Do you know what?
So 8 is new.
Like,
Yeah.
I want spectral theory specifically, but I also like, pardon?
Anything
I
operates.
did this.
Yeah, like spectral theory I use really good, or like complex analysis if I can tell that it's the area that I specifically like. So like any more like conformal maps or Mobius transformations or that kind of shit.
So you just search spectral
Theory, I have one at Loughborough.
It's the I'm pretty sure we've
King's College.
no, I'm pretty sure the next topic in also is spectral theory, isn't it?
A spectral operator.
Yeah.
What else?
Well, we're looking at a continuous spectrum of like.
Subelliptic operators and harmonic.
Is there one
Isn't that Birmingham?
Birmingham one?
Yeah, we added a bunch more.
Yeah, all with competition funded.
Yeah, it's not good enough, is it?
Funded. University of York, although chemistry.
Yeah, so in fact,
Spectrum.
let's continue. In fact, I just forgot to write this on my notes. So this part was really missing. So what? So we still have to prove that this. which means that this absolute value of f plus g to the power p must be integrable. So the integral of this has to be finite, so we have to find some kind of upper bound for this. And okay, if we take a point x in x, then f of x plus g of x to the power p, this is bounded by this is bounded by 2 times the maximum of f of x and g of x, right? F plus g, if I take the larger of the two and take that twice, then that's going to be larger than f of x plus g of x. So 2 times maximum f of x comma g of x to the power p is an upper bound for this. And then so this gives me a factor 2 to the power p, and then maximum of mod f to the power p well, the maximum of these two, it's either going to be f or it's going to be g, right? So if it's f of x, then I'll have this, and if it's g of x, I have g instead of f here, so I can just add the two together, and that only makes it larger. And now the sum of f and g is bounded by 2 integrable things. So this holds for every x. So we can integrate this inequality so the integral of f plus g to the power p is less than 2 to the power p times integral f to the power p plus integral g to the power p and then the integrals on the right hand side are finite because f and g were assumed to be in LP, and that's why f plus g to the power p is integrable. Yeah, so this was missing, sorry. Was that clear? Okay, so this really completes the proof now.
Yeah, I did, but I think it's. No, I don't think I do. It was. I was just trying to work out like this. F plus g to the p minus 1 to the q is the same as f plus g to the p.
Oh yeah, that's just because of this.
Yeah, yeah. Okay.
Because this cancels this denominator. Okay. Okay, so this concludes the section about integral inequalities, and the next section is called theory of LP spaces. And in this section, we're going to take these curly LP spaces and turn them into actual vector spaces with an actual norm. Right? We've already done some work. We've shown a triangle inequality of this LP norm. But I told you last time that this LP norm isn't really a norm, because if the LP norm of a function is 0, then the function does not have to be 0. It's only 0 almost everywhere. So we're going to introduce new spaces in this section called LP with a non-curly L. And these are going to be normed vector spaces and even Banach spaces, as we will prove. So, yeah, and the first definition introduces these spaces. So let X sigma mu be a measure space, and P between 1 and infinity and now we introduce an equivalence relation on these LP spaces. Defined as follows: F is equivalent to G if and only if F is equal to G almost everywhere. Okay, so we just identify all functions that differ on a set of measure 0. And then LP of X sigma mu is defined to be the curly LP of X sigma mu modulo this equivalence relation. So elements of the new LP space are equivalence classes of functions which differ only on sets of measure 0. Let Herne be the set of equivalence classes okay, and on this set of equivalence classes we can define a scalar multiplication and sum, and that turns it into a vector space. So the sum of two equivalence classes, as always, is defined by choose a representative of the first equivalence class, choose a representative of the second, add the representatives, and then take the equivalence class of the sum. And we're going to show in a minute that this is actually well defined. And for the scalar multiplication, we do the same thing. So the definition is not finished yet, so define sum and scalar multiplication like this, where f and g are finite valued representatives of the classes f and g, and lambda is a real number. And finally, for f in LP, define the norm of f to be the p norm of a representative. Okay, so for the my notation is this for the new LP spaces. For the norm, I will always write norm index LP, and for the old LP spaces, I'll just write index P. That's how we've always denoted it. So the new LP spaces, the norm will have an index LP. Okay. And now the next lemma says that this definition actually makes sense and is useful. Lemma 5.12, LP of x sigma mu are normed vector spaces over the real numbers. Okay, so to prove this lemma, we have to prove several things. First, we have to prove that this addition and scalar multiplication are well defined. Second, we have to prove that the axioms for a vector space are satisfied by these two operations. And third, we have to prove that this new LP norm is actually a norm in the sense of normed vector spaces. And we're going to start with well-definedness. Okay, so let's start with the sum. F plus G was defined to be, well, by this formula, where f and g are finite valued representatives. Okay, so the first thing to note is that finite valued representatives always exists, right? We have to be able to choose them. So finite representatives always exist because any representative of such a class is a function in the old LP space and we've seen already that such functions are finite almost everywhere. So you can just choose, so you can always choose this function such that it's finite everywhere, because you can just choose any representative of such a class, and then the set where it's infinite is a set of measure 0. On that set you can just put it equal to 0 if you want, and you still remain within the same equivalence class. And then you have a finite valued representative. So that you can always do. Second, class of F plus class of G is well defined. So we have to show that if we choose two different representatives for these classes, then this right-hand side always gives the same thing, right? This sum should only depend on the equivalence class, not on the representative. So let's just take two different representatives. Let the class of F be the same as the class of G. F prime. And class of G be the same as the class of G prime. Then, well, what does this mean? Class of F equal to class of F prime by definition just means that F and F prime are equal almost everywhere. So then F is equal to F prime almost everywhere, and G is equal to G prime almost everywhere. But this implies immediately that F plus G is equal to F prime plus G prime almost everywhere. Right? Because the set where these are not equal is a null set. The set where these are not equal is also a null set. So if I remove the union of these two null sets, then the sums are going to be equal on the complement of this union, which is still almost everywhere. Because the union of two null sets is a null set. Okay, but this is the same by definition as class F plus G is the same as class F prime plus G prime. So this addition is well defined. And for the scalar multiplication, it's very similar. So I'm not going to do that on the blackboard because it's very similar to the previous one. Okay, so this was well definedness. The second part. Is to show that LP is actually a vector space, but this is just a simple calculation basically. Now that we know that the sum and the scalar multiplication are well defined, it's just a bit of labor to verify this, and I'm not going to do this on the blackboard. yeah, one comment I'm going to make is that this uses Minkowski's inequality because part of being a vector space is, you know, if f is in LP and G is in LP, then f plus G has to be in LP again, and that was precisely one of the statements of Minkowski's inequality. Okay, so and the third part of the proof is to show that the LP norm is actually a norm. Okay, and to prove this, we have to check three things. First, the triangle inequality. But this is precisely Minkowski's inequality, right? So this we've already proved. The second part is positive homogeneity. So if we have the norm of lambda f for some real number lambda, then this has to be the same as absolute value of lambda times norm f. And so by definition of the scalar multiplication, this is norm of equivalence class of lambda times f. Okay. And now by definition of the norm, this is the same as the old p norm of lambda f. And now for the old p norm, the p norm of lambda f is the same as absolute value of lambda times the p norm of f. And by definition, this is the same as absolute value of lambda times the LP norm of the equivalence class of f. And this is precisely the positive homogeneity that we wanted to show. Okay, so we have this. And now the last point. If the LP norm of this equivalence class is 0, then the class itself has to be 0. Well, equivalence class, norm of equivalence class of f being 0 by definition is the same as the p norm of f being 0. But this implies, as we've seen, that f is 0 almost everywhere. But this is the same as saying that the equivalence class of f is 0. So in this new space LP, it is true that if the norm of an element is 0, then the element itself has to be 0. This is the reason why we've done all this, this whole definition of LP spaces, to make the old LP norm into an actual norm. Okay, so we've shown that the new LP spaces are vector spaces and that the new LP norm is actually a norm. And this completes this lemma. Okay, are there any questions? Okay, so there's one remark about this definition. First, so in this new space LP, the elements are equivalence classes of functions, and in particular, equivalence classes of functions have no values at any point x, right? So so it makes no sense, for example, it makes no sense to write down something like this, equivalence class of f of x or something. So really, yeah, all we know about these equivalence classes is that they contain functions that differ only on a set of measure 0. But it could be any set of measure 0. So at one particular point, an equivalence class has no value. And nevertheless, in practice, people usually don't distinguish between a function in LP between functions in LP and their equivalence classes. I'm really sorry about this chalk. So for example, instead of this equivalence class of f in LP, people just write f in LP, but what they actually mean is this. So in practice, people just, in the notation, they just omit these square brackets because it's easier to read and to write. So if you open textbooks, you will often see this. So remember that if someone writes this, they actually mean this. Okay, and I don't know how much sense it makes to make examples about this. So because these equivalence classes, I mean, you can't really write them down explicitly for any example. Now we can try. So for example, if we take the real numbers, the Lebesgue measurable sets and the Lebesgue measure, then the equivalence class of the characteristic function of the rational numbers is the characteristic is the equivalence class of 0, right? So in the new LP space, this equivalence class is just the 0 element. This is equal to 0. Or if we take the Dirac measure at 0, for example, then any function which is 0 at 0, for example x squared, the equivalence of this will be the equivalence class of 0. So any such function is just 0 in the new LP space. Actually, in this case, you can write down this equivalence class explicitly. So the equivalence class of 0 is just the set of all functions which are 0 at 0. So maybe this gives some intuitions into how these new LP spaces work. But really in practice, understanding these equivalence classes and yeah, that's not the most important thing, because if you write down integrals, the integral can't see sets of measure 0, right? If two functions disagree on a set of measure 0, then the integrals are the same. So whenever we compute integrals, it doesn't really matter whether we talk about the function or its equivalence class. So and that's the reason why people just write f instead of f in square brackets. Because in most applications it doesn't really matter which one you're talking about. Okay. Okay, so the next lemma gives us an additional property of the new LP spaces. So we've already seen that it's a normed vector space, which is very nice. And the next lemma says that it's actually a Banach space. So Cauchy sequences in the new LP spaces converge. And the proof is a little bit technical. So let X sigma mu be a measure space. P between 1 and infinity, and let Fn, equivalence class of Fn, be a sequence, a Cauchy sequence in LP then there exists a function f, well actually an equivalence class f in LP of X sigma mu such that the LP norm of f minus Fn goes to 0. So in other words, a Cauchy sequence in the new LP space has a limit in the new LP space. Okay, and in the proof, again, we have to distinguish p equal to infinity and p less than infinity. But the ideas of the proofs are similar. So we'll start with the case p equal to infinity. Okay, so now Fn is a Cauchy sequence with respect to the L infinity norm. So in particular, we can do the following. For every k in n, there exists a number nk such that norm of Fn minus Fm is less than 1 over k for every mn larger than nk. So this just follows from the definition of a Cauchy sequence, basically. You pick some epsilon. In this case, epsilon is 1 over k. Then, if I make n and m large enough, then the norm of this difference I can make less than epsilon. And then, well, we just do this for every k, and we get this statement. And this norm is of course the L infinity norm. Okay, and by definition of this L infinity norm, this means that Fm of x minus Fn of x in absolute value is less than 1 over k almost everywhere. So say for every x in x minus a null set ek, Okay, so this is because the essential supremum of Fm minus Fn is less than 1 over k. So by definition of the essential supremum, Fm minus Fn is less than 1 over k almost everywhere. Okay, so we have these null sets Ek where this inequality might fail. And then, because these are countably many, their union is still a null set. So let's call this union E. And then pointwise, the sequence Fn of x is a Cauchy sequence in R. For every x in x minus E. Okay, so we start with the infinity norm being satisfying this estimate with 1 over k. Then we get this pointwise estimate almost everywhere with the null set depending on k. Then we take the union of all these null sets, remove it from x, and then for all the remaining points, Fn of x pointwise is a Cauchy sequence in R because it satisfies this thing. Okay, and we know that the real numbers are complete, so in R, this sequence has a limit. So, Cauchy sequence in R, thus limit n to infinity Fn of x exists almost everywhere, right, in x minus E. But then we can do the following. We can define a function f to be the limit n to infinity of the characteristic function of x minus E times Fn of x. Okay, so on x minus E, Fn of x converges, so the limit exists. On E, this product is just 0, so the limit exists as well. So this sequence converges everywhere, and we call the limit f. Okay, and now we go back to this inequality. Fm minus Fn is bounded by 1 over k. We call this star. And now in this inequality, we let m tend to infinity. Right, we can do this now because now we have this limit function f. So we get that if we send m to infinity here, then fm becomes an f, while fn just stays there. So this becomes f of x minus fn of x is less than 1 over k for every x in x minus e and for every n larger than this capital Nk from the beginning. Okay, but this is precise. So this, yeah. So and this is basically it. So now we can take the essential supremum over x. On both sides, and then we get that the infinity norm of f minus fn is less than 1 over k, infinity norm. And well, this is precisely the definition of convergence, right? So this implies that also the new LP norm, so the norm of the class of f minus the class of fn, L infinity goes to 0 as n goes to infinity. So this finishes the case p equal to infinity. And again, there's not much time left. So let's take a step back and look at what we did, what the strategy was. We started with this L infinity norm, then we passed to this pointwise estimate, and then we used the completeness of the real numbers to get a Cauchy sequence in R. And then, because we know that the real numbers are complete, for these point values, we got a limit for free. And then this limit was translated back into a function in LP, L infinity in this case, and that's how we got our limit element. And yeah, we'll have to stop here. Next time we're going to do the case p less than infinity, and the idea and the strategy will be more or less the same. Again, we will start with the LP estimate, go to pointwise values, use completeness of the real numbers to get this limit element in LP. So that's what we're going to do next time. So thanks for your attention and have a nice weekend, and see you on Wednesday.